Welcome to Eduno's practical session of conversion of a galvanometer into an ammeter and voltmeter. In this session, we take a galvanometer of known resistance and figure of merit and then we convert it into an ammeter and voltmeter of desired range and then we verify the same. Before going to the experiment, let us go through the aim and the apparatus required to perform the experiment.
The aim of this experiment is to convert the given galvanometer into an ammeter and voltmeter of desired range and to verify the same. The apparatus used in this experiment are a Western type galvanometer, a voltmeter of range 0 to 3 volts, a battery eliminator, two one-way keys, resistance box of 10,000 ohms, resistance box of 200 ohms, a rheostat, a screw gauge, half meter scale, and milliammeter of range 0 to 50 amps, and connecting wires.
First we start with the conversion of galvanometer into an ammeter. Let us say we want to convert the galvanometer into an ammeter of range 3 amperes. As you know that a galvanometer gives full deflection for very small current. So to increase the range of galvanometer, we need to connect a small resistance in parallel to the galvanometer. This resistance is known as shunt resistance. So let us calculate the shunt resistance required to convert the given galvanometer into an ammeter of range 3 amperes.
Required shunt resistance S is given by Ig into G by I minus Ig. Here, Ig is the current required for full scale deflection in galvanometer. This is given by N into K, where N is the number of divisions in galvanometer and K is the figure of merit of the galvanometer. G is the resistance of galvanometer, that is 47.80 ohms, and I is 3 amperes as we want to convert the galvanometer to ammeter of range 3 amperes. Therefore, S is equal to Ig into G by I minus Ig. That is, S is equal to 0.01169474 ohms. Let us consider a copper wire as the shunt resistance wire. So, we need to find out the length of the wire required to provide the shunt resistance S equal to 0.0116974 ohms. We have a formula to find the length of the wire required. L is equal to pi r square S by rho, where r is the radius of the wire, S is the shunt resistance required, and rho is the specific resistance of copper. Here, we need to find the radius of the wire with the help of a screw gauge. Diameter of the wire is equal to main scale reading plus least count into circular scale coincidence, which is 0 plus 0.001 into 71, which is 0.071 centimeters. Half of the diameter gives us the radius, which is 0.071 by 2, which is 0.000355 meters. Therefore, L is equal to pi r square S by rho, that is 3.14 into 0.000355 whole square into 0.0116974 divided by 1.7 into 10 power minus 8, that is equal to 0.2722225 meters. L is equal to 27.22 centimeters. Cut the wire 2 centimeters more than the calculated length, as we lose some length while making connection. Here is the copper wire of 0.01169474 ohm resistance.
Here we got shunt wire of required resistance. Now we connect this wire in parallel to the galvanometer. Now the galvanometer is converted into an ammeter of range 3 amperes. After that, we verify the readings shown by the converted galvanometer with that of standard ammeter. To do so, we connect the converted galvanometer in series with the standard ammeter along with a power supply and a rheostat. So, let us make the connections as per the circuit diagram. Connect the positive terminal of the power supply to one end of the rheostat. Then from the other end of the rheostat to the positive terminal of the converted galvanometer. And from the negative terminal of the converted galvanometer to the positive terminal of the standard ammeter. And from the negative terminal of the standard ammeter to the negative terminal of the power supply. Now the connections are completed. Here the converted galvanometer has 30 divisions. 30 divisions are equal to 3 amperes. So each division gives us 0.1 ampere. And in the standard ammeter, each division is equal to 0.05 amperes. Now let me summarize the connections for you. Here positive terminal of the power supply is connected to one end of the rheostat, and from the other end of the rheostat it is connected to the positive terminal of the converted galvanometer, and from the negative terminal of the converted galvanometer to the positive terminal of the standard ammeter, and from the negative terminal of the standard ammeter to the negative terminal of the power supply. Now switch on the power supply and then adjust the rheostat so that some current passes through the circuit. Here in the converted galvanometer, the deflection is 5 divisions. Therefore, the reading is 0.5 amperes. And in the standard ammeter, the deflection is 10 divisions. So, the reading is 0.5 amperes. Note these values in the observation table. Here you can observe that the reading shown by the converted galvanometer and the standard ammeter are same.
Deflection in the galvanometer theta is equal to 5. Corresponding current reading in the converted galvanometer is equal to 5 into least count. Least count LC is equal to 0.1 amperes. That is equal to 5 into 0.1. Current in the converted galvanometer is equal to 0.5 amperes. Standard ammeter reading is equal to 0.5 amperes.
For more observations, we repeat the same procedure by changing the current using the rheostat, and in each case we note down the values of the converted galvanometer and the standard ammeter, and then we compare them.
For a galvanometer of deflection 5 divisions, the current reading in the converted galvanometer is 0.5 amperes and the standard ammeter shows a reading of 0.5 amperes. Similarly, for the galvanometer deflection of 10 and 15, the values of current readings in the converted galvanometer and the standard ammeter are as follows.
Therefore, we have successfully converted a given galvanometer into ammeter of range 3 amperes. Now, we move on to the conversion of a given galvanometer into voltmeter. Here, we take a galvanometer of known resistance and figure of merit, and then we convert it into voltmeter of desired range, say 3 volts. As you know that a galvanometer can be converted into voltmeter by connecting a high resistance in series with it. So let us calculate the series resistance required to convert the given galvanometer into voltmeter.
Galvanometer to voltmeter. Required series resistance R is equal to V by Ig minus G, where V is equal to 3V, as we want to convert the galvanometer to voltmeter of range 3 volts. Ig is the current required for full scale deflection in the galvanometer. That is equal to N into K. Here, N is the number of divisions in galvanometer and K is figure of merit of the galvanometer. G is the resistance of the galvanometer. Therefore, knowing the values of V, Ig and G, we calculate the value of series resistance. R is equal to V by Ig minus G, that is equal to 4040.40 ohms. When you round off this, series resistance R is equal to 4040 ohms.
Now, we know the required series resistance is 4040 ohm. This resistance is obtained by using a resistance box. So, take the resistance box and adjust the resistance to 4040 ohm. Then, we connect this resistance in series with the galvanometer. Now, the galvanometer is converted into voltmeter of 3 volts range. After that, we have to compare the readings shown by the converted galvanometer with that of a standard voltmeter. To do so, we need to connect the converted galvanometer, standard voltmeter, rheostat and the power supply according to the circuit diagram. Connect the positive terminal of the power supply to one end of the rheostat. And then negative terminal of the power supply to the other end of the rheostat. Now we connect the converted galvanometer in parallel to the rheostat. And finally, we connect the standard voltmeter in parallel to the rheostat. Now, we have completed the connections. Now, let me summarize the connections for you. Here, positive terminal of the power supply is connected to one end of the rheostat. And the negative terminal of the power supply is connected to the other end of the rheostat. And one end of the converted galvanometer is connected to one end of the rheostat. And the other end of the converted galvanometer is connected to the upper end of the rheostat. And the positive terminal of the standard voltmeter is connected to one end of the rheostat. And the negative terminal of the standard voltmeter is connected to upper end of the rheostat. Here, converted galvanometer, standard voltmeter and the rheostat all are in parallel to each other. Here, 30 divisions of the converted galvanometer is equal to 3 volts. Therefore, each division is equal to 0.1 volt. And in the standard voltmeter, each division is equal to 0.05 volt. Now, switch on the power supply and adjust the rheostat so that some potential difference is applied across the circuit. Here, the deflection in the converted galvanometer is 9 divisions. Therefore, the reading is 0.9 volt. And in the standard voltmeter, the deflection is 20 divisions. So, the reading is 1 volt.
Deflection in the galvanometer theta is equal to 9. Corresponding voltage reading in the converted galvanometer is equal to 9 into least count. Least count LC is equal to 0.1 volts. That is 9 into 0.1. Therefore, voltage in the converted galvanometer is equal to 0.9 volts. Standard voltmeter reading is equal to 1 volts.
For more observations, we repeat the same procedure for different values of potential difference applied across the circuit, and in each case we note down the readings shown by the converted galvanometer and the standard voltmeter, and then we compare them.
For a galvanometer of deflection of 9 divisions, the reading in the converted galvanometer is 0.9 volts and the standard voltmeter shows the reading of 1 volt. Similarly, for the galvanometer deflection of 18 and 25, the values of voltage reading in the converted galvanometer and the standard voltmeter are as follows.
From the observations, we can notice that the readings shown by the converted galvanometer and the standard voltmeter are almost the same. Therefore, we have successfully converted the given galvanometer into voltmeter of range 3 volts.
The connections should be neat, clean and tight. The cell should have a constant EMF all through the experiment. The ammeter and the voltmeter used for the verification should preferably be of the same range as the range of the conversion. The diameter of the wire to be used for the shunt resistance should be measured accurately. The length of the shunt wire used should neither be too small nor too large. Initially, a high resistance from a resistance box R should be introduced in the circuit to avoid any damage to the galvanometer. Value of required series resistance should be calculated accurately.
Now we are able to convert a galvanometer of known resistance and figure of merit into an ammeter and voltmeter of desired range without any doubt or hesitation. Thank you for watching this video.